Hello everyone and welcome to our next lesson. In this video, we'll be discussing air pollution control technology. We will be discussing the sources of air pollution, its effects to both humans and the environments, and how do we prevent or mitigate air pollution. Let us start with a brief discussion on RA 8749 or the Philippine Clean Air Acts of 1999. This provides the legal framework for comprehensive air pollution control. Here are some of the salient points of RA 8749 and its implementing rules and regulations, that is DNR Administrative Order 2000-81. First, and the most important, is the declaration that we have the right to breathe clean air. This is a very important declaration in the Act because that means that we all have the right to access clean air. RA 8749 also established the Ambient Air Quality Guideline values and standards for both ambient air and for industrial spaces. Also, we have the requirements of SEMS for potential pollution sources. SEMS stand for Continuous Emission Monitoring Systems. These are required to be placed in stacks wherein criteria pollutants might be generated. We will be discussing more of criteria pollutants later. You will commonly see SEMS in the stack gas of combustion power plants such as coal and diesel power plants. They are continuously monitoring for the levels of criteria pollutants. Also, we have the ban on incineration. It was explicitly stated in RA 8749 and its implementing rules and regulations that the incineration of waste cannot be practiced in the Philippines. However, the small-scale open burning, often seen in rural communities, and is also colloquially called as siga or pagsisiga, is not prohibited under RA 8749. Pagsisiga or small-scale open burning is often the way of solid waste disposal in rural communities. In this law, we also have emission standards for motor vehicles. These are the maximum pollutant levels that can be emitted by motor vehicles and their engines. Also, we have the prohibition on smoking inside public spaces and public transport. That is because cigarette smoke is still considered as air pollution. And finally, we have the regulation of fuel and fuel additives. This law cements the ban on leaded gasoline. That's why if you take a look at gasoline stations all over the country, they are only offering either diesel or unleaded gasoline. That's because in the past, we used to have lead in our gasoline to improve its performance. Under RA 8749, lead as a fuel additive is prohibited. Now, before we dive further into air pollution, let us first define the difference between pollutants and contaminants. These two terms are often used reversibly. However, there is an important distinction between these two terms. A pollutant is a naturally occurring substance that becomes harmful because of above-average concentrations. That means that it is naturally occurring, but human activities have introduced excessive concentrations of this substance. So even though it is naturally occurring at elevated concentrations, it still poses risks and dangers to the environment. In contrast, a contaminant is a harmful substance that is not naturally occurring, that is introduced to the environment. Therefore, a contaminant is a foreign substance. It is not naturally occurring. Okay? Even though they have different definitions, both are a result of our actions, either our failure to secure our waste or our indiscriminate use of our resources. Earlier in our lesson, I have mentioned about criteria pollutants. Let us define what are criteria pollutants. These are air pollutants that are commonly seen in urban spaces and are used as indicators of air quality. We have 6 criteria pollutants. We have carbon monoxide, particulate matter, that is either PM10 or PM2.5, ground level ozone, lead, nitrogen oxides, and sulfur oxides. Carbon dioxide is technically not a criteria pollutant but is considered as a pollutant in its separate class. We will be discussing all of these pollutants later. Here is the provided National Ambient Air Quality Guideline based on RA 8749 and its implementing rules and regulations. Here we can see some concentration values for the criteria pollutants both in the short term and the long term. These are the maximum permissible values of the criteria pollutants. If you are exposed to values of the pollutants that are presented in this guideline, that means that those concentrations are already hazardous. We have here for PM10, sulfur dioxide, nitrogen dioxide, ozone, carbon monoxide, and lead. Normally, we have different values for long-term and short-term exposure. That's because some of these are acutely toxic while some are chronically toxic. Now, since we are talking of air pollution, we have to define the scales of air pollution. That's because the broad term of air pollution is being used to refer anything that is not supposed to be in the air. However, we need to quantify the scale of pollution to make it useful for assessments, planning, and remediation. It's either is it a small scale pollution or a large scale pollution. In this table below, we have different phenomena and we have their scale. We have indoor or microenvironmental pollution. These are typically in the household level, so these are indoor scales. Next, we have neighborhood air quality. This is typically in the barangay or in the sitio level in the Philippines. We also have urban air pollution with scales encompassing cities, regional air pollution with a larger scale, acid rain or deposition with a given scale here, stratospheric ozone depletion which spans several thousand kilometers, and finally we have greenhouse gas emissions also spanning several thousands of kilometers. These scales of air pollution gives you an idea of who should be concerned regarding air pollution. Let's say for example, for greenhouse gas emissions, all of us should be concerned because it spans a very large area. It's not just localized to one area such as for urban air pollution. Okay, so for smaller scales, the effects are usually localized to places, while for larger scales, the effects and impacts can be felt by many people. Now, to understand how pollutants are being dispersed into our air, we first need to understand how our atmosphere behaves. An understanding of how the atmosphere behaves is important in the study of air pollution. Air pollution is largely dependent on factors such as location of sources, weather, climates, elevation, and meteorological conditions. Those factors dictate the dispersion and distribution of pollutants. An analogy for the understanding of the role of atmospheric dynamics into air pollution are the appearance of these stack gases. These stack gases normally come from combustion, and you can think of them as point sources of pollution. Point sources meaning that they can be easily identified and located, and they can be tagged as a potential source of pollution. Let's first talk about the atmospheric temperature profile, or how does the temperature vary in our atmosphere. The layers of the atmosphere have different temperature profiles. As you can see in this figure here, we have the different layers of the atmosphere: troposphere, stratosphere, mesosphere, and thermosphere. Of course, regarding air pollution, we are most concerned on the troposphere because this is the section that we largely use. The air that we breathe comes from the troposphere, and the pollution that we release also largely stays in the troposphere. Generally, the temperature and pressure in the troposphere decreases as the altitude increases. You can see in this graph that as the altitude increases, in the troposphere, the temperature decreases. That is until we reach the tropopause. The tropopause is the boundary between the troposphere and the stratosphere, after which we have a layer of constant temperature. After which, as we traverse the stratosphere, we can see an increase in temperature as the altitude continuously increases. That is until we reach the stratopause, wherein there is another region of constant temperature, and then the mesosphere also displays the same temperature profile as the troposphere. That is, as the altitude increases, the temperature decreases. And for the thermosphere, as the altitude further increases, the temperature generally increases. That is because this is already in the vicinity of outer space. Now, bringing our focus back to the troposphere, the ratio of the temperature decrease with the increase in elevation is called the lapse rate. The lapse rate is also the slope of the graph between altitude and temperature. The normal average values are 6 to 7 degrees Celsius per kilometer. This is what we call the dry adiabatic lapse rate. That means that for an increase of 1 kilometer in altitude, the temperature should decrease by 6 to 7 degrees Celsius. This is also the reason why places with higher altitudes, such as Baguio City and Tagaytay City, have lower temperatures, while the lowlands or those that are near sea level often see elevated temperatures. This kind of atmospheric temperature profile, wherein the temperature decreases as the elevation increases, allows warm air to continually rise. For example, if warm air is coming from ground level, warm air will continue to rise against cold air. That's because of the buoyancy differences between warm and cold air. Warm air tends to float, while cold air tends to sink. If the warm air carries pollutants, which is common if the warm air is coming from a city, It is therefore dispersed above, far from ground level activity. That means that if we are generating pollutants on ground level wherein there is warm air, that has the potential to rise. And when pollutants rise above, that means that they can be dispersed to a larger volume of air above our atmosphere. It also means that we are carrying pollutants away from us, thereby preventing the accumulation of pollutants on ground level. Now we have two kinds of lapse rates. We have a positive lapse rate, and it is desired to keep the continuous rise of warm air from the ground. A positive lapse rate means that warm air from the ground will rise. A negative lapse rate, on the other hand, means that the temperature increases as elevation increases, thereby preventing warm air from the ground from rising. That means that the air parcels containing urban pollution would remain on the ground and it will not float up into the atmosphere and be dispersed. Based on this illustration here, we have the exhaust stack, which is the point source of pollution. If we have a negative lapse rate, this warm air would actually sink down and not rise up. That's because for a negative lapse rate, as we increase in elevation, the temperature is also increasing. That means that our warm air will not be able to rise up. This kind of negative lapse rate presents problems in urban air pollution. Now let us dive deeper into what we call atmospheric stability, because the atmospheric stability will determine if we have a positive or negative lapse rate. The stability of the atmosphere dictates whether air parcels can rise or fall. This pertains to the vertical movement of air parcels. First, we have an unstable atmosphere. This encourages the vertical movement of air. So in a nutshell, we want to have an unstable atmosphere. This is the illustration of the graph of the elevation versus temperature for an unstable atmosphere. If you take a look at our environmental lapse rate or our actual lapse rate compared to the dry adiabatic lapse rate, we have a higher temperature decrease with regards to elevation for an unstable atmosphere. That means that if you have a warm parcel of air, it will be encouraged to go further and further upwards, thereby enhancing the dispersion of the pollutants. In contrast to that, we can have a stable atmosphere which prevents the vertical movement of air. If you take a look at the graph of the stable atmosphere here, our environmental lapse rate could either be slightly stable or very stable. If you take a look at the slope of the very stable atmosphere, this is essentially the opposite of the dry adiabatic lapse rate. That means that instead of our warm parcel of air rising, our warm parcel of air would remain on the ground, and we don't want a stable atmosphere. Some of the worst periods of air pollution happen when the atmosphere is stable because the pollution cannot go up, it stays on the ground. Now, the final type is a neutral atmosphere which neither prevents nor encourages the vertical movement of air. This happens when the environmental lapse rate is almost identical to the dry adiabatic lapse rate. That means that parcels of air or parcels of pollution stay where they are produced. If we have a stack that is 50 meters tall and it is producing stack gas with pollution, the pollution stays at 50 meters in elevation. Those are the implications of a neutral atmosphere. Our illustration here also shows us the difference between an unstable and a stable atmosphere. For an unstable atmosphere, our pollutants or our parcels of air are encouraged to go up. In this case, they are illustrated as clouds. While for stable atmospheres, normally the parcels of air just travel horizontally and not vertically. Now we have to discuss the concept of thermal inversion. In the case of a stable atmosphere, vertical mixing and movement is discouraged because of the presence of a thermal inversion layer. The thermal inversion layer is what prevents our warm air from rising to the upper levels of the atmosphere. If you take a look at the graph between the elevation and temperature for an inversion layer, the inversion layer represents an anomaly in the normal temperature profile. If you take a look at the dry adiabatic lapse rate, the temperature decreases as the elevation increases. For the thermal inversion layer, the temperature increases as the elevation increases. Normally, the thermal inversion layer is sandwiched between two layers of the atmosphere with a normal lapse rate. For example, this inversion layer is sandwiched between an unstable layer and another unstable layer. Take a look at these figures for an enhanced understanding of thermal inversion. Under normal conditions or under an unstable atmosphere, we have a demarcation between warm air, which is near the ground, and cold air, which is far up the ground. So the warm air parcels that are normally carrying pollutants are simply carried to the cold section of the atmosphere. There are no hindrances to this flow because of the unstable atmosphere. If we have a thermal inversion layer, what you see here is we have warm air that is sandwiched between two layers of cold air. So what happens is the parcels of air, normally containing pollutants in the ground, cannot float past the warm air. They can only rise up to the same level as the inversion layer. This would present problems if the thermal inversion layer is really low. That means that all of our pollutants would simply bounce back to us, and that would be very problematic. These are examples of thermal inversion layers. If you take a look at this city here, you can see a visible smog, and that smog likely comes from the city here. Instead of the smog or smoke to be dispersed higher up in the atmosphere, what you see here is the clear demarcation of the thermal inversion layer. That means that the pollutants cannot go past that thermal inversion layer. The concept of the inversion layer is much more visible in this second photograph here. You can see that the smoke coming from the ground cannot disperse past this layer here. That means that there is a thermal inversion layer present along here. You can also see that the smoke is going back to the ground. This trapping of the pollutants presents a real danger to the residents of this place. Thermal inversion traps air pollutants on a region and prevents its dispersion and dilution in the atmosphere. This is common in valleys in the morning because in the morning, surface temperatures are often cold, and then the rising of the sun promotes a warm layer to cover areas such as this. And that's what causes thermal inversion layers. Now, another meteorological concept that we have to be familiar about is called the mixing height. The mixing height or mixing depth also determines the maximum height that a parcel of air can rise. Mixing heights function the same as a thermal inversion layer. Mixing heights are dependent on the dry adiabatic lapse rate, while thermal inversion layers are not. That is the main distinction between the two concepts. If you take a look at the graph here to your right, on the first figure, we have the graph of the dry adiabatic lapse rate, that is the yellow-green line, and also we have the graph of the environmental lapse rate, that is the orange line. There seems to be a point wherein the two lapse rates intersect. That intersection is actually the mixing height. The mixing height gives a limit on how far or how high can a parcel of air float. This mixing height represents the point wherein the buoyancy of the warm air rising is the same as the buoyancy of its surrounding air. This is different from the thermal inversion layer because an inversion layer does not depend on the dry adiabatic lapse rate. If you take a look at the graph here, there seems to be conditions wherein thermal inversion layers can occur. For example, in this small portion of the graph here, there is a thermal inversion layer because instead of the usual decrease in temperature as we increase our altitude, this presents the opposite. So this could be a thermal inversion layer. If you go back to the environmental lapse rate of the previous graph, this lower part here is also a thermal inversion layer. This is a thermal inversion layer that is very close to the ground, and these types of inversion layers have implications on how we release pollutants into the air. Now let's discuss the effect of the atmospheric stability on the release of pollutants. As established earlier, whenever we are releasing pollutants to the air, even though they are well within the limits for industrial emissions, we still have to consider how will those pollutants be dispersed into the atmosphere. That is to prevent it from coming back into the ground level. Let us start for the case of unstable atmospheres. For an unstable atmosphere, looping occurs. The turbulence caused by the release of stack causes it to behave chaotically. This results to a minimal exposure to pollution on the ground level because the pollutants are eventually dispersed upwards. This is an illustration of looping. Assume that the wind direction is from left to right. So for looping, as soon as the stack gas is released from the stack, it is turbulently dispersed into the atmosphere. And since we are under an unstable atmosphere, this stack gas would continue to rise up. Therefore, this minimizes the amount of pollutants that would return to the ground. If we take a look at the temperature profile for looping, we have a lapse rate that has a greater value than the dry adiabatic lapse rate. The behavior of looping is often what we want for the release of stack gas. Let's have the opposite. For a stable atmosphere, fanning occurs. The stack still travels horizontally according to the prevailing winds, but stays at a horizontal layer. Vertical mixing is minimized. Therefore, the stack gas would just travel horizontally along its designated layer. The layer where it travels depends on the buoyancy forces of the stack gas and the buoyancy forces of its surrounding. If we take a look at the temperature profile for fanning, We have here the dry adiabatic lapse rate, and we have here the lapse rate for a stable atmosphere. This is a negative lapse rate. That means that the vertical mixing of the stack gas is discouraged in this type of release. The fanning of stack gas could present problems if somewhere along the line, the stack gas starts to descend into the ground level. That is one of the dangers of fanning. Even though vertical mixing is minimized, if the gas is cooled enough, it can start to mix with the lower layers of the ambient air. Next, we have the case for the neutral atmosphere. We have coning. The stack forms a cone that increases its diameter as it goes farther from the source because of the cooling and expansion of the stack gases. The atmosphere does not influence the rising and the falling of the stack gas. If you take a look at the temperature profile for coning, our environmental lapse rate is the same as the dry adiabatic lapse rate. Therefore, the stack gas is neither encouraged nor discouraged from mixing with the other layers of the atmosphere. Coning can also present some problems because the lower part of the cone would eventually reach the ground levels. Therefore, pollution would still reach the lower levels. For the next case, if we have a low-lying inversion layer, lofting occurs. The stack is designed to be a little higher than the average height of the thermal inversion layer, resulting to a stack that has very little chance to disperse in the ground. This can be exploited in places with well-defined and low-lying inversion layers. If you go back to our example earlier, this one, you can see that in the lower elevations, there is a thermal inversion layer. This part right here is a thermal inversion layer. That means that we can exploit this for the purposes of lofting. All we have to do is to build a stack that goes beyond this thermal inversion layer. The net effect is all of your pollutants contained in the stack would have very little chance to reach the ground because of the thermal inversion layer. Your pollutants are basically dispersed above the thermal inversion layer. Therefore, they are not trapped below the inversion layer. If you take a look at the temperature profile here, this is the inversion layer up to an elevation of 1 kilometer. Therefore, the stack has to be released above this in order for that to be considered lofting. In some cases, the thermal inversion layer is very high such that we cannot reach it with our conventional stack. In such cases, lofting may not be possible. Okay? So lofting is only possible for some geographies or for some cases. And finally, we have the opposite of lofting. If there is a low-lying inversion layer, but the stack releases below the layer, fumigation occurs. This is the worst way to release stack gas as the pollutants will be trapped in the vicinity of settlements. Fumigation is normally what happens if you start an open fire early in the morning. What happens is the smoke rises, disperses, and then goes back to the ground. That's because you have released the smoke below the inversion layer. If you take a look at its temperature profile here, we have the environmental lapse rate showing the thermal inversion layer, which is above the release points of the stack. This is very dangerous because all of these pollutants would be trapped under the inversion layer and all of those pollutants would go back to the ground. Therefore, we are much more exposed to the dangers of the pollutants under the condition of fumigation. Remember that this is the worst case scenario for the release of stack gas. Now let's discuss the sources and impacts of air pollutants. Earlier, we have described the criteria pollutants. Now we will be discussing their sources and their impacts to both us humans and our environment. Let's start with sulfur oxides or SOx. Sulfur oxides could either be SO2, sulfur dioxide, or SO3, sulfur trioxide. Sulfur oxides are often implicated in the occurrence of acid rain. That is when sulfur oxides are dissolved into rainwater and they fall into the surroundings. That causes severe damage to both man-made structures and the natural environment. Major sources of SOx pollution are coal-fired power plants that use high sulfur coal and motor vehicles through the combustion of the fuel. There is a little sulfur presence in the fuel, although that is regulated. And also, there are some types of coals that are low-grade, meaning that they have a high concentration of sulfur. The combustion of those fuel sources releases SOx into the atmosphere. SOx is what we call an acid gas because when this combines with water, you form an acidic water. SOx can acidify bodies of water, destroying ecological balances. This can result into fish kills, as shown here, and can also result to the proliferation of a single species in an aquatic ecosystem that is very dangerous to a balanced ecosystem. It can also ruin soil chemistry and mobilize heavy metals. If acid rain falls into soil, the soil chemistry can be drastically changed. That means that we are also affecting the microbial population of the soil, which is important in maintaining carbon compounds in the soil. It goes without saying that acid rain caused by sulfur oxides are also very dangerous for agriculture. Acid rain can ruin crops in one instant. Also, acid rain can mobilize heavy metals in the soil. That is because the mobility of heavy metals are pH dependent. At high values of pH, most heavy metals are insoluble. That is, they are present in their stable forms such as their hydroxides or their carbonates, which have very small solubilities in water. Therefore, even though they are in the soil, they are not mobilized into the water, so they present very minimal risk to the groundwater. However, if you change the pH of the soil, let's say for example, there is acid rain and the soil pH decreased drastically. The decrease in pH converts those carbonates and hydroxides which are insoluble into the soluble ionic form of the heavy metals. Therefore, those heavy metals are now mobile. That means that they can be transported through the groundwater or can be absorbed by the plants, and that is very dangerous. That means that we are introducing more heavy metals into our cycles. Those are the effects of acid rain to our environment. Inhalation of SOx can cause irritation, burns, and difficulty in breathing. Basically, these are all respiratory effects. A severe exposure to SOx can burn the lining of our lungs and can cause irreparable damage. Next, let us have nitrogen oxides or NOx. Nitrogen oxides are the primary ingredients for the formation of photochemical smog along with VOCs. VOCs are volatile organic compounds. We will be discussing VOCs later. This is an example of a photochemical smog. A photochemical smog is a corrosive mixture of vapors that presents dangers to the respiratory systems of humans and animals as well as on crops and ecosystems. Photochemical smogs usually contain ozone, another criteria pollutant, as well as peroxyacyl nitrates and nitric acid. You can commonly see photochemical smog in big cities such as this, wherein the air gets a hue of dark brown. Ground-level ozone is often produced from the photochemical reactions involving NOx and VOCs. Ozone is another criteria pollutant that is very dangerous in the ground level. Vehicle emissions and high-temperature combustion are the primary sources of NOx in our environment. So therefore, we can expect elevated levels of NOx in urban settings. That is why photochemical smog is also common in urban cities. NOx is also an acid gas, and it also plays its role in acid rain together with SOx. Next, we have carbon monoxide. Carbon monoxide causes asphyxiation in humans and animals under prolonged exposure, even in small concentrations. Basically, carbon monoxide mimics the function of oxygen. It binds into the hemoglobin in our blood, but carbon monoxide is not released by hemoglobin. Therefore, when you breathe in carbon monoxide, instead of you supplying oxygen to your vital organs, your blood simply binds to carbon monoxide and it becomes unable to carry oxygen. That deprives you of oxygen and that leads to asphyxiation or death due to suffocation. Carbon monoxide is hard to detect in enclosed spaces without dedicated measuring devices because it is odorless, colorless, and tasteless. Therefore, you cannot determine if an enclosed space contains appreciable levels of carbon monoxide. Carbon monoxide is generated largely from the incomplete combustion of fuel, mostly from vehicles and diesel generators. That is the reason why diesel generators should never be operated inside enclosed surfaces. They should be operated outside wherein there is open air. That's because the carbon monoxide should be dispersed outside and not be accumulated inside. The incomplete combustion of fuel from motor vehicles are also very dangerous, especially for the vehicles that are idling in enclosed garages. You can gather a lethal concentration of carbon monoxide that would be very dangerous to anyone that is trapped on those conditions. The signs of carbon monoxide poisoning are also often attributed to just overall sleepiness. So you might just be feeling a little bit sleepy because of the lack of oxygen, but then when you sleep, you never wake up because you have been poisoned by carbon monoxide. In the environment, carbon monoxide can also take part in photochemical reactions with volatile organic compounds and NOx. Therefore, carbon monoxide is also a precursor to photochemical smog. Next, we have particulate matter or PM. PM is measured in two distinct size classes, that is PM10 or PM2.5. PM10 are suspended particulate matter with sizes less than 10 micrometers. PM2.5 are considered as potent carcinogens, especially for respiratory parts, because of their ability to penetrate deep in your body. So PM2.5 are particulate matter with sizes less than 2.5 micrometers. Also, PM2.5 are deadlier because they are not filtered by common face masks. They also penetrate the mucous lining of the lungs, which causes irritation or, in some cases, even cancer or damage to the lungs. To visualize the size of such particulate matters, we have an illustration here. This brown part is actually human hair, which measures around 50 to 70 microns. Let's say, for example, that the width of this human hair is 50 microns. That means that we can fit 10 particles with 10 microns in diameter. Therefore, the largest particle size possible in PM10 is 5 times smaller than the diameter of the human hair. Now, let's consider PM2.5. The largest particle in PM2.5 can fit 4 times in the width of a single PM10 particle. So if we are talking of PM2.5, that means that these are already very, very, very tiny particles. These are imperceptible to the human eye. We won't even know if we are inhaling PM2.5. Now, in addition, beyond PM2.5, we still have the ultra-fine particles. The ultra-fine particles are categorized as particles measuring less than 0.1 microns in diameter. These are now very, very tiny particles that will have no problem adhering to the linings of our lungs. That's why particulate matter is one of the most dangerous component of urban air pollution. We cannot detect it, but we are continuously inhaling it. Common sources of particulate matter include motor vehicles. The incomplete combustion in the engines of motor vehicles generate almost all of the criteria pollutants. They generate SOx, NOx, they can generate particulate matter, they can also have volatile organic compounds, and they have carbon dioxide and carbon monoxide. The particulate matter in the exhaust of such motor vehicles are characterized as soot. Those are carbon particles that are commonly generated from smoke. They are actually the visible part of smoke. Particulate matter can also be present in our homes. The clothes that we wear, the floor of our houses, carpets, air conditioners, electric fans, all of those can generate and perpetuate particulate matter. An emerging form of particulate matter that is of utmost concern right now are microplastics. Microplastics are already in the air that we are breathing, even though we are at the safety of our houses. Particulate matter in the form of microplastics can be produced by our clothing, especially those clothings that are made of synthetic fibers such as polyester. That is just one thing to keep in mind. Next, we have lead. Atmospheric lead primarily comes from coal-fired power plants or smelters and combustion of leaded fuel. In the past, we have added tetraethyl lead into our gasoline to increase its performance. This is what we call an anti-knock fuel additive, meaning it enhances the performance of engines. However, the combustion of tetraethyl lead as an additive in fuel generates atmospheric lead, which is very dangerous for us. That's why tetraethyl lead is now banned for use in common motor vehicles. If you notice, whenever you are buying gasoline, it states that that gasoline is unleaded gasoline. That means that it does not contain any lead. Now, tetraethyl lead for those unleaded gasolines was simply replaced by an alternative that does not contain lead. However, even though tetraethyl lead is now banned for use in motor vehicles, we still have remaining users of leaded gasoline. The remaining users are piston engine aircrafts and some race cars and marine engines. Therefore, the use of leaded gasoline is still prevalent in our modern society. Some of the airplanes still use leaded gasoline, as well as some of the ships that transport our cargoes overseas. You can then imagine that the sources of atmospheric lead traces back to aircrafts and marine ships. As for the effects of lead into our body, lead is highly toxic in the human body. It targets the kidneys and the nervous, circulatory, and immune systems. A continuous exposure can lead to organ failure and other complications. Continuous exposure can lead to organ failure and other complications. Lead in our body behaves like calcium. That's why it is common for lead poisoning patients to have defects or abnormalities with their bones, because lead is basically replacing the calcium in their bones. Lead is also persistent in the environments and can magnify and accumulate in the food chain. It displays both biomagnification and bioaccumulation. That means that lead can persist for a very, very long time in the environment. It can be magnified in the food chain, and it can even reach our stomachs if we are eating the top predators of the food chain. This is a common issue for heavy metals in general, such as lead, mercury, cadmium, and other heavy metals. As we go up the food chain, they are being transferred and concentrated. If you have read reports that shark meat contains very high concentrations of heavy metals, that is a possibility because sharks are top predators of their food chain. If heavy metals are being ingested by the lower members of the food chain, that would be accumulated and magnified as you go up the food chain and ultimately reach the sharks. Next, we have the ground level ozone. Now, we have two types of ozone. We have ground level ozone and stratospheric ozone. If the ozone is present in the stratosphere, then it is very helpful. It is a helpful absorber of damaging ultraviolet radiation in the stratosphere. That is why we have always been concerned about the ozone layer. We have banned and phased out substances that can deplete the ozone layer. That's because the ozone layer is in the stratosphere and it is very far from us. If the ozone is in the troposphere and worse if it is at ground level, it is a dangerous gas that causes respiratory irritation and damage in humans. Also, it damages crops and vegetation. Basically, ozone is a very strong oxidizing agent that can oxidize a majority of substances that it touches. That's the reason why photochemical smog is not only unsightly and not only irritating to the lungs, it can also damage our structures. Ozone in the ground level is largely generated from the photochemical reaction of NOx, VOCs, and CO, as we have discussed earlier. Photochemical meaning UV radiation is involved in the process. These kinds of reactions are actually radical reactions, meaning that they are unstable and they can occur very fast. When ultraviolet radiation strikes an ozone molecule, it has the potential to generate a simple oxygen molecule, that is O2, plus an oxygen radical. That oxygen radical is very reactive and that gives ozone its powerful oxidizing properties. For the next class of pollutants, we have volatile organic compounds or VOCs. Now, VOCs are technically not included in the list of criteria pollutants, but they are still common in urban places and they can still be dangerous. These VOCs are a class of organic compounds that are easily released to the air, either as small particles or as vapors. Volatile organic compounds are easily volatilized. Common VOCs that we encounter include formaldehyde, hydrocarbons, acetone, alcohols, and dichloromethane. Some of these are industrial solvents, so they can escape the process as vapors or they can be generated inside of our houses from various activities. For example, formaldehyde and hydrocarbons can leach out of some of our plastic products. Acetone and alcohols are common solvents at home, so they can still be volatilized. Some of these VOCs are carcinogenic, mutagenic, and teratogenic, meaning that they can cause cancer, or they can damage our DNA, or they can cause damage to an unborn child, leading to deformities. They are generated from the volatilization of solvent residues or from the incomplete combustion of fuels and solid waste. In the urban setting, VOCs are normally hydrocarbons or remnants of uncombusted fuel from the incomplete combustion of engines. VOCs are the reason why there is a distinctive smell to the exhaust of vehicles. There is also a reason why we have the natural aversion to avoid the smell of combustion. That's because the VOCs that are being produced there are very harmful to our respiratory system. Next types of pollutants, we have the ozone depleting substances. Ozone depleting substances or ODS are a separate class of pollutants because they are very specific in their action. These are substances that catalyze the degradation of stratospheric ozone. Stratospheric ozone is the one we are trying to save. Common ODS are chlorofluorocarbons or CFCs. I'm sure you are familiar with CFCs, as well as carbon tetrachloride, methyl chloroform, and hydrochlorofluorocarbons or HCFCs. HCFCs were once touted as the replacements for CFCs, but then we found out that HCFCs are also ozone depleting substances. These were once commonly used for purposes such as refrigeration, air conditioning, propellants in aerosol cans, fumigation, and other related purposes. Their manufacture, selling, and use are now banned under the Montreal Protocol. The Philippines is a signatory to the Montreal Protocol. That is why ozone-depleting substances now has a chemical control order in the Philippines. A chemical control order for ozone-depleting substances means that we can no longer import, manufacture, sell, or use commercial quantities of these ozone-depleting substances other than for use of devices that still need these ozone-depleting substances. These substances are being phased out in our country as a result of the chemical control order. Shown in this mechanism is how CFCs catalyze the degradation of stratospheric ozone. We have the CFC molecule. When it is hit by ultraviolet radiation, we can detach a chlorine radical from that CFC. That chlorine radical binds with ozone, which is O3, and then it separates to ClO and O2. O2 is simply just oxygen gas. It's just plain oxygen. Now, if the ClO molecule happens to be hit by an ozone radical, which is rather common in the stratosphere because remember, the degradation of ozone generates ozone radicals. So if an ozone radical hits the ClO, it binds to the ClO, and what happens is we again generate oxygen or O2, and we also free the chlorine radical. This chlorine radical could then cycle back to the start of the process and then destroy more ozone molecules. The process repeats itself until the chlorine radical is stabilized or it is deposited back into the lower layers of the atmosphere. But before it gets stabilized, it has the potential to destroy hundreds and hundreds of other ozone molecules. If you consider a big scale of these kinds of events, it is easy to see why ozone-depleting substances have punched a big hole into the ozone layer in the past. But after the enactment of the Montreal Protocol, we do have some good news because that protocol is directly responsible for the restoration of the stratospheric ozone layer. The hole in the ozone layer is now healing. That means that we are restoring its natural capability to filter out harmful UV radiation from the sun. And finally, the most destructive classes of air pollutants are what we call the greenhouse gases or GHGs. Greenhouse gases are air pollutants that so far have the widest and most consequential effects for our civilization. The most common and most widespread greenhouse gas is carbon dioxide. All of us are familiar with carbon dioxide because it is the stuff that we breathe out, and that's also the same stuff that plants utilize for photosynthesis. However, if we disrupt that balance of respiration and photosynthesis, what we have is a very big excess of carbon dioxide in our atmosphere that is responsible for the greenhouse effect. Greenhouse gases have varying potentials to trap heat inside our atmosphere, and this is called the greenhouse effect. Now, the greenhouse effect is a natural phenomenon, but the very fast rate of addition of carbon dioxide to our atmosphere makes the greenhouse effect as one of our worst enemies. In excessive levels, they can cause an abnormal accumulation of heat and a rise in global average temperatures. This phenomenon is called global warming. As the global average temperature increases, drastic shifts in climate and weather patterns emerge. This is called climate change. These three terms are all very different terms. So you need to be careful whenever you are using greenhouse effect, global warming, and climate change. Please take note of their definitions. Let's go through them one by one. First, the greenhouse effect. The rich variation in species of micro and macroorganisms in Earth is largely attributed to the hospitable temperatures in Earth achieved by the natural greenhouse effect. Without the greenhouse effect, we will not be able to flourish. Earth will become very, very cold, such as the case with Mars. Mars has a very thin atmosphere. It does not have enough gases to trap heat. However, if we have an excess of greenhouse gases, such as the case of Venus, our twin planet, it can trap so much heat that our surface temperature would be inappropriate for life. When anthropogenic CO2, methane, and N2O and other greenhouse gases were introduced, the greenhouse effect introduced a multitude of problems for our planet. That includes global warming and climate change. This is an illustration of the greenhouse effect. Our atmosphere acts as a clear blanket wherein it can let light and heat pass through. It can also let light and heat escape, but the presence of greenhouse gases in our atmosphere ensure that some of that heat energy is bounced back to our planet. That maintains our hospitable, warm temperature. However, since we have an excess in greenhouse gases, what happens is there is less and less heat energy that is escaping, and more of that energy is being trapped inside, therefore warming our atmosphere. That warming of the atmosphere leads to global warming. The concentration of atmospheric CO2 has long fluctuated, but the increase in carbon dioxide during our modern time has not yet shown signs of peaking or slowing down. The deniers of climate change and global warming have long argued that the concentration of carbon dioxide has always been fluctuating. This graph shows the atmospheric carbon dioxide concentration for the last 800,000 years. you can see some periods of increase and decrease periodically. That means that there is a dynamic balance of carbon dioxide happening in our atmosphere. You can also see that if we take the average value of those carbon dioxide levels, we would be somewhere around in between 200 and 250 parts per million average concentration in the atmosphere. However, if you take a look at this point here up to the peak here represents the past 200 years of developments of our world. That is from 1800s forward. The current atmospheric CO2 concentration in 2018 was already beyond 400 ppm. That is way beyond our usual average between 200 and 250 parts per million for the past 800,000 years. That is not normal. Even if we zoom to a smaller time period, let's take a look at this graph here wherein we are showing the atmospheric CO2 concentration for the past 12,000 years. You can see that there is a steady concentration of carbon dioxide that lies between 250 and 300 ppm. But over the last 200 years, our carbon dioxide emissions have skyrocketed and it shows no sign of slowing down. Now, what is responsible for that sharp increase in carbon dioxide emissions? The answer is our industrialization. Our use of coal, oil, and gas as our main sources of energy are the biggest contributors to the increase in our CO2 emissions. The total carbon emissions of the world over the past 200 years have made a mark in the global average temperature anomaly. The global average temperature anomaly is the difference between the actual temperature and the average temperature. That means that if you have a positive temperature anomaly, that means that the temperature is hotter compared to the average. And if you have a negative temperature anomaly, it is colder than usual. If you take a look at this graph for the average global temperature anomaly, over the past 200 years or so, our global temperature anomaly started to increase. We have crossed the threshold of 0 degrees Celsius temperature anomaly. 0 degrees temperature anomaly means that our temperature is perfectly average. It's perfectly within the normal range. Starting from 1990, our global temperature anomaly just continued to increase. We are now 0.8 degrees Celsius warmer than the previous average temperatures. 0.8 degrees Celsius of temperature change might not seem large, but keep in mind that this is an average temperature anomaly. If we take a look at the situation of the world, we can actually see unequal warming patterns, meaning that the warming is not the same in all parts of the world. This temperature anomaly map shows the uneven distribution of warming. It seems to be occurring faster on the poles. That means that the temperature anomaly on the north and south poles are on average larger than those found on the equator and on the other parts of the world. That means that it is getting hotter faster in our reservoirs of ice. And that is very dangerous because if our ice reservoirs all melt, the average sea level of the world would rise and some parts of the world would be submerged underwater. That is one of our concerns that is directly impacted by global warming. So now that we are already on the 0.8 degrees Celsius global average temperature anomaly, what can we expect in the future? The continuous exponential increase in carbon emissions are projected to cause a global average temperature anomaly of 4.1 to 4.8 degrees Celsius by 2100 or by the end of this century if no actions are done. The change of 4.1 to 4.8 degrees Celsius in the temperature anomaly is very devastating to all of us. What would happen is sea levels would rise, islands would be underwater, there would be mass extinction in the oceans and in the lands, and we will be unable to grow our food. That is, if we are not taking action. We have here some projections on what would happen with our current policies. For our current policies, we can expect temperature anomalies of 2.8 to 3.2 degrees Celsius by the end of this century. This temperature anomaly is still too high. That's why our world leaders are continuously pushing for more and more policies that targets to reduce our greenhouse gas emissions. We have what we call 2-degree pathways and 1.5-degree pathways. These are both from the Paris agreements. If we stick to our 2 degrees and 1.5 degrees pathways, we can bring back our atmospheric carbon levels. We can bring back our atmospheric carbon levels back to their levels in 1990. That is the best case scenario, and that should be the scenario that we are rooting for in the future. With all of those impacts and problems that I have mentioned, it is no secret that climate change is currently the biggest problem of our civilization. That's because it affects absolutely everyone, though unequally. People on the lower margins or on the lower classes of our civilization will be affected much more harder than the rich people. That is a basic inequality in our civilization. However, it will still affect every single one of us. Here are some of the biggest impacts that we are expecting if we cannot keep our promise of keeping our greenhouse gas emissions down. We can expect sea level rise from the melting of our polar ice caps. We can expect more powerful and destructive weather systems that includes typhoons in the Pacific Ocean and hurricanes in the Atlantic Ocean. We have already been experiencing stronger typhoons here in the Philippines, and that is because of a warming planet. Typhoons and hurricanes are both powered by warming oceans, so if you continue to increase the temperature of oceans, the oceans would then continue to pump out stronger and stronger typhoons and hurricanes. Another impact that we can expect is ocean acidification and disruption of aquatic ecosystems. As the concentration of carbon dioxide in our atmosphere increases, that carbon dioxide can actually neutralize or disrupt the acidity balance of the ocean. Basically, if the ocean becomes acidic, majority of the life forms in the ocean would perish. Some of them may survive because they can adapt to the changing pH of the oceans, but the reality is majority of those aquatic creatures cannot adapt fast enough to cope with the changing pH of the ocean. A mass extinction event on our oceans would greatly affect our way of living. That event would ensure that none of our food would come from the oceans. Also, the mass extinctions or mass die-offs in oceans would present even bigger problems in the decomposition in all of those masses of aquatic organisms. Their mass decomposition could release large amounts of methane, and methane is a much more potent greenhouse gas, therefore further worsening the greenhouse effect, and in turn global warming, and in turn climate change. A warming planet would also mean that our food production will be disrupted. That is because in the future, our rainfall patterns may not be as reliable as previously, and it might become harder and harder for us to extract both surface water and groundwater for irrigation. Another possibility is accelerated extinction, not only on the oceans but also in our terrestrial ecosystems. Not all of the organisms on Earth are suited to very warm temperatures. And finally, we can also expect unpredictable episodes of El Nino and La Nina. Even though El Nino and La Nina are natural patterns in climates, if we have a warming planet, episodes like this would become very unpredictable and would be very catastrophic. Now, with all of these talks about greenhouse gases, global warming, and climate change, we need to make sure that we understand that carbon dioxide is not the only one to blame for all of this mess. Even though carbon dioxide is the most common and the most widespread greenhouse gas, there are still lots of other substances that exacerbate global warming. They are characterized by their global warming potential or GWP. Basically, the value of the GWP states how much worse is this substance compared to carbon dioxide. For example, carbon dioxide has a global warming potential of 1. That means that it is basically equivalent to carbon dioxide, which makes sense because it is carbon dioxide. If we compare that to methane, which has a 100-year global warming potential of between 16 to 26, this means that methane is approximately 16 to 26 times worse than carbon dioxide. That means that methane is much more potent than carbon dioxide in trapping heat in our atmosphere. So while most of us are focused solely on carbon dioxide, what we don't know is there are also other gases that are contributing to the greenhouse effect that are much worse than carbon dioxide. That's why in some industrial operations, such as in landfills, it is much more better for you to combust methane and for it to become carbon dioxide than for it to remain methane in the atmosphere. That's because carbon dioxide is a less potent greenhouse gas than methane. Aside from methane, we also have other gases such as nitrous oxide or N2O with a 100-year global warming potential of 310, meaning it is 310 times worse than carbon dioxide. Also, we have hydrofluorocarbons or HFCs with a very high global warming potential, as well as perfluorocarbons and sulfur hexafluorides. Some of these substances are also ozone-depleting substances. Therefore, we really do not want them to be lingering in our atmosphere. The first 3 entries to this table, CO2, methane, and N2O, are the 3 most common greenhouse gases. Methane and nitrous oxide often come from the anaerobic decomposition of organic substances. The carbon in the organic substances could turn to methane when decomposed anaerobically, while the proteins or other nitrogen-based compounds can turn to nitrous oxide. It might surprise you, but our agricultural system actually contributes a big part of our methane and nitrous oxide emissions. Methane is mostly famous from being emitted by cows, such as our reliance to eating beef is harming our atmosphere. We eat more beef, therefore we have to produce more cows, and the cows generate more methane. That is a vicious cycle that will never stop as long as we are largely consuming beef. Nitrous oxide is also generated in agricultural operations wherein the anaerobic conditions of the soil can turn some of the nitrogen-based fertilizers into nitrous oxide. Now, with all of those talks about greenhouse gases, let us now take a look at some of the international treaties that aim to address global warming. The first one is the Kyoto Protocol. The Kyoto Protocol is an agreement of UN member states to adopt policies on mitigating and reducing greenhouse gas emissions. It targets a 5% average reduction in greenhouse gases compared to the 1990 level. The Kyoto Protocol is simply a collection of the promises of individual member states on how they plan to reduce their greenhouse gas emissions. The Philippines is one of the signatories to the Kyoto Protocol. Next, we have the amendment to the Kyoto Protocol called the Doha Amendment. The Doha Amendment updated the targets for reduction. After the target 5% reduction in the Kyoto Protocol, the Doha Amendment stipulated that the average reduction should be increased by 18% compared to the 1990 level. That is a significant reduction in greenhouse gas emissions. Again, the Philippines is also a signatory to the Doha Amendment. And finally, we have the most recent, the Paris Agreement. The Paris Agreement reinforces the goal to reduce global warming. Its primary aim is to keep global temperature rise to 2 degrees Celsius or lower within this century, and eventually limit the increase to 1.5 degrees Celsius compared to pre-industrial levels. If you remember earlier, we have presented scenarios on which what would happen if we limit our temperature increase to 2 degrees Celsius or 1.5 degrees Celsius. That would be our best case scenario. Basically, that means that our levels of greenhouse gas emissions are back to 1990 levels. The Philippines is also a signatory to the Paris Agreement. For the final part of this lesson, we will be taking a look at some of the technologies that we are currently using to prevent air pollution. Now, these are just some of the technologies that are being employed in the industry. There are some technologies for air pollution control that are very specialized and are not included in this list. Let's start with electrostatic precipitators or ESPs. The main purpose of an electrostatic precipitator is to gather particulate matter. That's why its target pollutants is particulate matter. Electrostatic precipitators are operated by applying charges of opposite polarities to plates which attract and collect particulate matter. Basically, particulate matter have surface charges, and by applying a charge on metal plates, we can rapidly precipitate particulate matter. If we will not be applying electrical charges, it would be very difficult for us to settle particulate matter. Some of them will never settle. That's why we have to apply electricity. This is an example of an electrostatic precipitator. We often see electrostatic precipitators in industries that generate particulate matter like coal-fired power plants and other milling and manufacturing industries. Next, we have baghouse filters. Baghouse filters also aim to address particulate matter. In these types of systems, air is forced to pass through layers of filters to trap suspended particulate matter. Basically, we are forcing them to settle by trapping them in a filter. This is an example of a baghouse filter wherein shown here is the direction of the airflow. So dirty air is introduced at the bottom and it is pressurized and it is forced outside of the filter. What comes out is cleaned air and then the particles are trapped on the inner surface of the filter which can be removed later. Next, we have wet scrubbers. Now, there are several classes of wet scrubbers and they can be designed or made to address different target pollutants depending on the industry. Wet scrubbers are typically used to target particulate matter, SOx, NOx, and CO2. If a wet scrubber is being used to address CO2, we call that a carbon capture system. In a wet scrubber, polluted air is contacted with sprayed water. So basically, water along with some other additives depending on the target pollutant is sprayed at the top and then the gas is introduced at the bottom. As the gas travels upwards, it is contacted with the water or the solution with additives from the top and that creates a chemical reaction that immobilizes your target pollutant. For SOx and NOx, lime slurry is commonly used to precipitate calcium compounds. So your absorbents introduced at the top contains calcium oxide, that is the main component of the lime slurry, and calcium oxide reacts with sulfur dioxide to produce gypsum, and it reacts with nitrogen oxides to form calcium nitrite or calcium nitrate. The precipitated compounds of calcium can then be used for other purposes such as for the manufacture of cements or for fertilizers. For carbon dioxide or for carbon capture, our absorbents are various amine solutions. We have monoethanolamine, triethanolamine, and other amines. This is one of the ways on how we can capture the carbon dioxide being generated by combustion. After capturing, we can then treat the absorbent solution to release the carbon dioxide in a controlled manner, and then we can use that CO2 for other purposes. Next, we have packed bed absorbers. Packed bed absorbers are basically the same as wet scrubbers, so these are simply modifications of scrubbers. Packed bed absorbers contain inert media that increases the contact area between the air and the absorbent. The inert media inside of the packed bed absorbers usually contain a high specific area such that we can greatly enhance the mass transfer characteristics between the liquid stream and the gaseous stream. Packed bed absorbers are commonly used for the capture of VOCs or for carbon capture. Next, we have adsorption beds. Adsorption beds normally target volatile organic compounds and SOx. In this technology, the polluted airstream is passed through a bed of activated carbon or other adsorbents materials. Basically, adsorbent materials are substances that are very porous and have a high affinity for substances in the air. For example, for activated carbon, organic compounds have a high affinity to adsorb in the pores of activated carbon. Therefore, we can capture organic compounds in the air by trapping the organic compounds in the pores of the activated carbon. In these types of systems, the activated carbon is normally granulated. We call that granular activated carbon. And that gives us a very, very high specific surface area of the pores in relation to the weights of the activated carbon. The only downside to using adsorption beds is that when the adsorbents is already spent, meaning that it's already saturated with your VOCs, you have to replace your adsorbents and you have to dispose of it. There are also some adsorbents that can be regenerated, but their regeneration can be energy intensive. So most of the time, it is more practical to simply replace the adsorbent. And finally, we have thermal oxidizers. Thermal oxidizers are a family of pollution control technologies that have the same working principle. We simply combust the pollutants in the air to form carbon dioxide and water. The pollutants that are treated by thermal oxidizers are often hazardous air pollutants and VOCs. These hazardous air pollutants and VOCs are normally non-combustible at room temperature. But for thermal oxidizers, we are raising their temperature and we are introducing them together with a fuel so that they can be combusted. We have several types of thermal oxidizers such as direct oxidizers and regenerative thermal oxidizers. They just differ on the mode of operation, but their purpose are the same, to oxidize pollutants into carbon dioxide and water. So that is just a short list of some of the most common air pollution control technologies that are being utilized in the industry. Sometimes more than one of these is present, depending on what criteria pollutant are we addressing. So with our knowledge of the different types of air pollution control technologies, as well as our knowledge of how pollution is dispersed in the atmosphere, including our knowledge of the nature of the criteria pollutants, their effects and their sources, we are now better equipped at making decisions on how to treat with industrial air pollutants. I hope that you will be carrying this knowledge in your line of profession after you graduate. That's it for this lesson. I hope you have learned something. Thank you for listening, and as always, keep safe.